Okay, let's check the recording. Everything is going on great. So, share my slides. So, I think you guys must have gone through the lectures or lecture videos which are uploaded on the Moodle. Sorry, not Moodle, Swayam portal. So, yeah, please go through those lecture videos and slides that will help you guys to actually gain a deeper understanding of the subject more clearly. Okay. Of the course more clearly, and if there are any questions you are always welcome to ask them in the live interaction session, or you can always post it on the discussion forum also. So let's start. I think it's already 7:06 and more people will join in the meanwhile. Okay. So, good evening, everyone. I am Rohit. Welcome you all to this live LPTL session of the course Sustainable Power Generation System. This course is taught by Professor Pankaj Kalita and he is Associate Professor in IT Party. I am Rohit. I'll be taking this live interaction session. So, you please feel free to ask any questions if you have any doubts or anything related to assignments. Uh, you can always raise your doubts here or you can post your queries on the discussion forum. This is me and the methodology will be same. There will be a doubt clearing firstly in the discussion on the topics taught in the weekly lectures that I do in all my live interaction sessions so that you guys generally can have a good grasp or understanding about what has been taught in the previous lecture. And also if there are any doubt, I try to clear it on spot. Like if you have any questions, please feel free to raise them. Also, this lets me let me to interact with you guys also. So that is also a very good session so that more things can be discussed in this session apart from the topics which are taught. You can always use the discussion forum or the chat box freely. So starting from the hydro energy, so I think most of you guys must have been have a good understanding about what constitute a hydro energy. So anything that produces from a flow of water is hydro energy. So generally we utilize the flow of water to produce electricity in our ancient times. The flow of water was used also to produce like electricity was not a thing. So it can be also be used to have a mechanical work also. You can generate mechanical work by rotating some turbine or something. So that is something great concepts about utilizing renewable energy. So the kind of uh, leverage here is that water is freely or accessible resource available on this earth. So why don't you use the flow of water to generate electricity or power? So that can be utilized. So that is what is done in this hydroelectricity. So when we talk of hydroelectricity in India, so there are two classifications related to hydroelectricity. One is major hydroelectricity like big projects like okay, the hydroelectric plants which you see like Tehri Dam or some other dams are there. So these are big hydroelectric projects. So they are called large hydropower plants, and then you have hydropower projects which generate less than 25 megawatt of power. So these are very small power plants. So actually, what is uh, the kind of concept here? It goes that if you have to build a very large power plant, then you need a very large catchment area, a reservoir, and a big dam that actually damages the ecological sensitivity of the zone. So basically, when build a dam, these dams are to be built at some higher elevation level so that we can catch the we can utilize the kinetic energy of water coming to the dam so as to produce electricity. So that that actually requires to build these dams in some eco-sensitive zones also. So that actually creates a lot of problem uh, for like wildlife, the biodiversity, everything, and the people also. Like people are displaced, villages get lost. Sorry, villages lost a lot of land and their sustainable resources also. So the point here is that India is targeting. So we have small streams. So some of them are perennial, so some of them are not so perennial. They are seasonal in nature, but the flow is quite high. So you can utilize those flows to generate electricity also, like small hydropower projects, and that can be utilized on the spots or maybe connected to the grid. Okay, so this was the concept actually thought of when designing a small hydropower projects. But if you see the small hydropower project, they still constitute a very small part of the like total renewable generation or total electricity generation is apart from total hydroelectricity generation, these small power plants contribution are still very less. So lot of efforts and push is going on these small power plants, but to install them and to get them the at some large scale implementation requires much of effort, and that effort has to be pushed throughout. I think in upcoming years you will see a lot of push towards these small hydropower projects. Okay, so basically, I think if we are going to discuss about hydroelectricity, so what is the focus of this hydroelectricity? So one thing is that it is 100% renewable because the flow of water is always there. It's a resource that is not going to uh, like dried up, or like fossil fuel. It is not going to end up. Okay. Second, to produce sorry to produce electricity from the hydro power plant is basically to uh, like it is environment friendly, because when you burn fossil fuel to generate electricity, it does have CO2 emission, CO emission, and all those greenhouse gases are produced, which are harmful for the environment also. So that we are avoiding when you are using a hydropower plant for generating electricity. Okay, improve socio-economic conditions. So this is a point. It can be debatable because when big dams are built, they actually displace a lot of people. But yeah, because of those dams, you will see more towns are coming up in the vicinity of that area. So more economic opportunities are there. Because availability of electricity, it does push up the industrial reforms and everything. So a kind of balance is maintained and it is tilted towards improvement of the economic condition. But yeah, you cannot ignore the thing that it does have a very it does hamper the society in a negative way also. And power requirements of remote and isolated area. So sorry. I will give you an example for this. So we have a country called Bhutan. So it's a very remote country surrounded by mountains, everything. Or you can say take up some areas of Nepal. So those are very remote, and if you want to build a power plant, so that will require a lot of effort and everything. But there the water is available, perennial source of water is there. So you can build a dam there, and then you can fulfill the water requirement there itself for the remote or isolated area. You don't have to go and build a power plant. Then you have to take fuel like coal or natural gas there to burn and then supply electricity. So this is what is being said here when it says power plants are remote and isolated area. Now, one thing this classification you have to remember, because maybe questions can be asked in the micro hydro up to 100 kilowatt, mini hydro is 100, 1 kilowatt to 2 megawatt, and then the small hydro is 2 megawatt to 25, and then big large power plants are basically greater than 25 megawatts. And if you want to measure the potential energy of water, so that is basically converted to potential energy of water. Because of height of the water at some elevated levels, the water flows through a channel to the turbine, and then it moves. When it says hydraulic prime mover, it is basically talking about the turbine that is moved by the water. Okay, so there are different types of prime movers are there. So in this case, it is hydraulic prime mover, that is turbine. So we'll discuss some of the turbines used in the hydroelectric power plants also. And then it is converted to shaft power, because turbine is connected to a shaft and coupled with a generator. So shaft power is basically rho g q h into n. So rho is not present here at in density. You can assume density of water as 1000 kg per kilowatt. So P will be in kilowatt. Okay. Okay. So the first hydroelectric power plant with a capacity of 130 kilowatt was installed at Darjeeling in India. So Darjeeling, I think Darjeeling is in West Bengal, hill station, West Bengal hill station. Then you must have flow of water, so you can always build a electric hydroelectric power plant there to capture that flow and convert it to electricity. So if you have any questions regarding this. Any questions, any queries from you guys? Okay, so no problem. If you have any queries, please feel free to raise it in the chat box. So I'm always available to answer your queries. And maybe during the lectures, I won't be able to hear you guys or see your queries. So you can always type it here in the chat box, and in between lectures, I will try to read the chat box and then I will answer your queries. Okay. So basically, after evaporation, percolation, and other losses, the amount of rainfall flows through the catchment area on this. So basically, catchment area is the surrounding area. So it's a big area through which the flows is collected to a channel or river. Okay, that is the catchment area. So a river has a basin, and that basin is basically the expanded basin. Is type of, you can understand it as a catchment area. On the surface of the earth is known as runoff. So runoff is basically total precipitation, whatever rain has been there, then some of the water will be lost as evaporation, and some of the water will be absorbed in the soil or may be lost here and there. So you subtract these evaporation losses from the total precipitation, that you will get the total runoff. So this is a question. Hydroelectric power plant has a catchment area of 100 kilometers square with an annual average rainfall of 80 centimeter in that particular area, and is used to generate power. So a total of 70% runoff and a mean head of 60 meter is available for power generation. So calculate the capacity of the plant, and if the plant is operated for 15 hours per day, find the energy generated in kilowatt hour per year. So I want you guys to solve this question. So uh, take some time and solve this question. Otherwise, I will solve this question for you. So this question has been directly taken from the lecture slide. So if you have gone through the lecture slides, you must be easily able to solve this question. Otherwise, because some of the questions in the exam or assignments will be like this only. So I want you guys to have a practice of these type of questions. Okay, so let me see if you guys are actually doing it. Jayesh has asked capacity of large hydropower plant. So, is there any question, Jayesh? Do you want to ask anything? Mm-hmm. No, no. Generally, they are categorized as large hydropower plants. Okay. So, because there are some subcategories also like medium hydropower plants, but really when you see like I think it's 200 megawatts or something for large hydropower plants or something. So generally you have to classify it as a hydroelectric power plants and then mini hydroelectric power plants. Okay, so small hydro SHP, small hydropower plants. So to make a difference, you take a 25 megawatt of the cutoff criteria. So that criteria is more important than other criterias, other subcategories. Okay, and are you able to solve this numerical which was there on the screen? Yeah, don't worry. Keep trying, and otherwise, I will solve it for you guys so that you can have a good grasp about how to solve these type of numericals. Okay, so let me see if you guys have. No problem. So let me solve it for you guys. So the problem is you need to understand that you have a catchment area of 100 kilometer square. So this is kilometer. So you need to convert it into meter square. Okay, and there is annual average rainfall of 80 centimeters. So that also has to be converted to meter. Okay, and then head is given So you can easily calculate the capacity and total runoff, like total runoff will be this into this, and because 70% of the total, like this is the actual precipitation, okay, but only runoff is 70%, like 30% is actually lost, like some evaporation or other losses will be there. So what you do, you calculate the water available for power generation. Okay, so I will say, okay, so you must have known why these extra 30 and 36 zeros, to convert it into meter square, and then you multiply it with 80 by 100, that is also in the meter, and then you multiply it with the runoff, like 0.7. So you will get the q value of q. Okay, so this is annual. Okay, so if you have to get the value of q in meter cube per second, so you need to divide this whole term by 24 into 365 into 3600. Okay, like in 1 hour 3600 seconds are there, one day 24 hours are there, and then 365 days. Okay, that will something come around 1.77 uh, meter cube per second. Okay, now you got the value of q here, so you know the formula, rho g h q. You know rho is 1000, g is 9.81, head is 60 meter, and then you also know the q here. So just multiply them, and then that comes out to be around 7. Okay, that comes out to be around 815 something point 3 kilowatt. Okay, so this is the capacity. Okay, now the plant is operated for 15 hours per day. Find the energy. Assume the plant is shut down for, so like in total days of operation is 365 minus 35. This is total days of operation of plant, and kilowatt is the power generated, and then you have to multiply it with kilowatt hours, so 15 hours per day. So that comes out to be around 4.03 into 10 to the power 6 kilowatt hour. That is, this much amount of electricity will be produced if you have this condition. Like a hydroelectric power plant has a catchment area of 100 kilometers square with an average annual rainfall of 80 centimeter. So this is quite a big unit, like 10 to the power 6 is like 40 million units of electricity will be produced from this hydroelectric power plant. So this is the capacity of the power plant. So you can imagine the amount of electricity that can be produced annually. Okay, should I go ahead, or is there any questions regarding this? Okay, Jayesh has raised a hand. Jayesh, sorry, I think I didn't unmute or something. Okay, so was it audible? Whatever I uh, showed you. Okay, don't worry. I will repeat actually. So I forgot to say unmute. Okay. Uh-huh. So no problem. These can be done. This can be easily. Okay. So actually, basically, what I was trying to say that. this hydroelectric power plant has a catchment area of 100 kilometers square. So that's a very big catchment area. Like if you imagine it to be square like 10 kilometer into 10 kilometer, so you have to convert it to meter square because units has to be same for the calculation. So to convert it into meter square, you just multiply it with 10 to the power 6, and this is in 80 centimeter. That is total annual average rainfall is 80 centimeter there, so that also contribute to the catchment area. So total flow, so catchment area into that annual rainfall, that is the total flow that you will be getting. So, and then some of them is lost, like 70% is only the runoff, like 30% rest is lost or evaporated. So you don't consider that in the total flow. So Q is basically 100 into 10 to the power 6 into 80 by 100 into zero point 0.7. And then you need to have a Q in meter cube. This is meter cube annually, but you don't want, because it's annual rainfall of 80 centimeter, but you don't want annual value. You want a meter per second value for the calculation of capacity. So you divide it by 24, like, sorry, you divide it by 3600, like 1 hour 3600 seconds are there in 1 hour, then in 1 day 24 hours are there, then in 1 year 365. Basically we are dividing it by the number of seconds in the year. Okay, so after dividing we get the value 1.77 or 1.78 meter cube per second. So you know the capacity of the plant value formula, rho GHQ. Rho you know 1000, G 9.81, head is given 60 meter, Q is 1.77 meter cube per second. So put those values and then you will get something as 815.3 kilowatt of the capacity of the plant. But it is saying ki now the plant is operated 15 hours per day. So you need to actually uh, find out the total amount of electricity generated in kilowatt hour per year. So for year, what you do, it's saying that 35-day plant is not working, per day 15 hours are there. So multiply 815 into 15 hours and then multiply the number of working days in a year. So you will get 4.03 into 10 to the power 6 kilowatt hours. That is 440 million units something is electricity is being produced annually from this configuration of the hydroelectric power plant. So that's a very great amount of electricity when you see this. Okay, so I hope that clears your doubt, Jess. And okay, so that's why I want you guys to actually have an approach to solving the numerical. So what I see that people generally don't go for slides numerical in the assignment questions. So that can look difficult, but these are not difficult. These are basically the questions which are based on the basic concepts which you learn in the slides. Okay. Now moving to the element of hydroelectric power plant. So if you see a hydroelectric power plant, I will explain it through this diagram. That is the perfect diagram to explain the hydroelectric power plant. So you see a hydroelectric power plant. This is the catchment area. This expands up to 100 kilometers square. So that's a very big catchment area. It may look small here, but this whole diagram is like a point in this catchment area. This catchment area is so big for any river or any flow. Okay, so you make a reservoir here that you see in and a dam here. Okay, so dam is actually created to make a reservoir so that you can generate electricity. Then there is this, and these gates are there in the dams. So these gates are opened and then water flows through this. This is penstock. Okay, and then it goes to a turbine that is prime mover. Then turbine is connected to a generator or alternator which produces a three-phase supply. Okay, and after turbine you have a draft tube. And then tail race is basically whatever water has been utilized, it flows through a channel or any flow that goes towards what you say in downward direction for some other usage. Okay, so that is tail race. Now draft, the usage of draft tube is basically quite a good concept actually, which has been utilized. So draft tube looks like this. Okay, the problem here is key, whatever water is coming here, it does have a very high velocity because of this flow in the penstock and the potential energy converting to kinetic energy. The draft tube has an area of A1 into V1 here and A2 into V2, that is total flow. Okay, so as the area is increased, so with continuity equation A1 V1 equal to A2 V2, so as the area is increased, area is small here, this V2 has to be decreased in the same proportion. So whatever V2 decrease is there, that is decrease in kinetic energy of the water, is basically transferred to the pressure energy. Okay, so this is what the concept of draft tube. So it does have a very low kinetic energy and high pressure energy, low velocity, high pressure. So what it does stop the like movement of air inside the turbine so that cavitation can be prevented, and other is that it does provide a good uh, actually the water to flow thoroughly throughout the uh, tail race. Okay, so this is one of the reason why draft tube is basically used. So reservoir is basically to store water during times of plenty for subsequent use in the times of scarcity. So now this is rainy season in India, so whatever water will be generated will be stored in the reservoir. So reservoir is basically when you go and visit a dam, you see a very large body of water. So that is a reservoir, and the catchment area may be 10 times or 20 times of that reservoir. So this is the amount of catchment area that is required to build a dam. And then dam is basically build up a height for power generation, also develops reservoir for storing water. So this is what dam does actually. Penstock is basically a pipe or conduit through which we supply water from dam to the turbine. Okay, and draft tube diverging discharge passage connecting runner with tail race to regain the kinetic energy. So draft tube has two functions. One, it is converts kinetic energy to pressure energy, and second, it does stop the air from going into the turbine so that cavitation is stopped. Okay, now elements of a hydroelectric power plant. So this is what we were studying here. It's like a top view. Now we'll see a side view of that. So from side view, what we see, this is the dam. This is the dam. Okay, this is the reservoir. This is the tunnel. Okay, then there is a surge tank. Surge tank are basically when you flow water through a tunnel, then pressure can go up and down because of some air present in there. So surge tank are there to store the water and also to make a constant flow of water throughout the penstock. So penstock is basically connecting this dam to the turbine here. This turbine rotates, and due to the coupling of generator, the electricity is produced. So spillways to relieve the reservoir of excess water in the reservoirs. Whenever there is excess water, so these water can flow through the dam and make damage. So spillways are there to actually let go of excess water. Powerhouse support the hydraulic and electric equipments. This is basically the powerhouse. Okay. Surge tank, when a governor reduces the rate of flow, like here, because it has to match the demands, electricity demands, governor has to match. So maintain the constant speed of the runner according to load variation. Water hammer occurs in the penstock. Okay, so this is what I was talking about, because when you have a sudden stop in the water, so water hammer can lead to damage to the pipes also. Sudden surge of water is reservoir and supplied during the increase in demand. So this is what surge tank is actually used. So Basically, I have put this diagram to have make you guys aware. It's more, this is basically like a schematic sketch, and this is more like a technical sketch, explaining the different technical constituents of the hydroelectric power plant. So this is weir. Weir is basically to maintain a constant flow throughout the channel. Okay, desilting is there. So this is kind of forebay is there. Forebay are made to make the water stored so that a constant water is flowed, and also the use of forebay and desilting tank is that key. It does help in desilting the particles in the water, so that actually has to desilted because that can impact the turbine itself. Even if there is a small dent on the turbine, the power generation capacity can be very much hampered, especially in case of reaction turbines, which I'm talking about. Temporary storage of water to be finally utilized for power generation, 2 minutes to 6 hours of storage is there in the forebay. Then you have penstock, then turbine, then there is tail race from here. This is tail race, this is draft tube generator, and then there is speed governor is there basically to match the electricity demand with the water flow so that a constant power can be generated. Frequency and voltage output of the generator depends on the shaft power. So this is actually true because whatever power shaft will generate, that will be converted to power in electricity generator. So this is what desilting dam to trap the silt and load and paper so as to minimize erosion damage to turbine. Designed to divert and maintain regulated flow in the channel for variable flow in the river. Temporary storage of water to be finally utilized. So this is how it looks like. So before going into this, and then I have a numerical that I want you guys to solve. So please have a look at this hydroelectric power plant layout, and if there are any questions, please feel free to write in the chat box. So now we'll move to the gross head. That is basically the difference between the headrest level and the tail rest level. So headrest level is at the dam level. So when you see a water here, I'll tell you through a diagram. So this is the headrest level. Okay, this level is the headrest level. Okay, the water level here, and then there is a tail race here. So that has to be measured. So this is the gross head is basically difference between the headrest level here and the grossless sorry tail rest level. Net head is basically it is the head available at the inlet of the turbine. So basically hg, that is gross head, and the whatever losses are there, that has to be subtracted. So losses is basically given by FLV for FLV square upon 2GD, that is flow through the penstock and other things. So that has to be taken into account. Hydraulic efficiency, runner power by water power. So runner power is basically this: whatever power the turbine produces and whatever power the water has gives the hydraulic efficiency. So there are different types of efficiency in the hydroelectric power plant. So don't, until and unless specified, always try to understand what is the efficiency which is talking about. So if no efficiency, the term is not specified, take it as overall efficiency. Mechanical efficiency is shaft power by runner power. So whatever uh, power is generated by runner, but whatever available at the shaft. Okay. Volumetric efficiency is volume of water actually tracking the runner and volume of water supplied to the jet. So we'll see in the later slides what does it mean. Overall efficiency is basically shaft power that is generated, shaft power is generated power, generator power, and the water power which has. So if you multiply the NH into NM into NV, you will get the overall efficiency. That's all. You can also get it from here. And water power is basically rho g HQ that we solved the numerical also, that and divided by thousands, so that gives you in the kilowatt. So solve this question. I want you guys to solve this question actually, so that solve that. Then we'll move to the turbines, and then turbine, then another question, then okay. So try to solve this question, and if there are any questions which you want to ask, please feel free to ask. Let me see if there are any questions. Okay, so no questions. So I want you guys to solve this question. So let's say it's 7:50. So by 7:50, I'll try to solve this question actually. Okay. Okay, let me see if you guys have actually made uh okay, so solve the question. No problem, I will solve it. Okay. Hello? Huh, yeah, same. 832.38. Okay. So average rainfall, meter per year, and then you have a discharge here. So you calculate it, and then 70% can be rainfall can be used as expected, load factor of 50%. So you know the discharge. Okay, so let me note it to be. How much was the discharge? 832 point. Okay, meter cube per second. So if you know the discharge, then I think everything is known. You have the load factor here. You have the head here. So rho G H Q into this load factor, power in kilowatt. So this has to be divided by 1000 if you want power in kilowatt. Assume head loss in the system is 8%. So 1 minus head loss, HL I can say. Okay. And then mechanical efficiency of the turbine is Nm and generator efficiency is Ng. Now just put the values and get the answer. Okay. Mm. 3211.55. No, I think 3211.55 kilowatt. Okay. So this, I was assuming this discharge is quite high. 832.38 meter cube per second is quite high. It should be around 8.32 or something. And that is what that's why I was calculating actually. You must have missed or something. So and then divided by 24 into 3600 into 365. So such high discharge at per second is quite too much high. Yeah, it is 8.32. Oh, they have done a mistake here actually. This is centimeter. 125 meter per year is quite a high rainfall. This is centimeter. So that is why I divided it by 100. This is centimeter, 125 centimeter. This is wrong value in the question. 125 meter of rainfall is impossible. Rainfall throughout the year generally measures in mm. Even 80 centimeter, 125 centimeter rainfall is quite high. Okay. So generally, rainfall are like 1100 mm or something. So in a season, so yeah, it can be in a year, it can be 80, 100 centimeter or something. So yeah, this is centimeter. Then rho GHQ, you have to just multiply all these values, this into this to get the overall efficiency, and then load factor. Okay, load factor you have to divide it here. Okay, this is an overall. I can say this. Okay, n overall is basically this into this. So this is not an overall. You have to this is head loss. So and actual efficiency of this is 1 minus 8%, that is 0.92. Okay, so that will be the correct answer. Ha, 0.92. Okay, so is it done? Okay, then impulse turbine. So I want you to actually have a look at the whatever has been taught in this interaction session up to this point. So if there are any question, please feel free to ask so that we can have a good discussion. And, okay, so you guys can actually go through these slides and then see if there are anything which you want to ask or any numerical question which are quite difficult and can't be solved by you guys. So you can always ask. So till then. Okay, so did you guys all had any doubt regarding this? No doubt? Okay, so yeah, Jayesh, is the answer to I don't know. Did you calculate? Huh, then it must be 274 or something. Okay, so don't worry if you have done it correctly. The answer is only what you have got it. Okay, I will not do some other type of calculation and then get the answer. Okay, so just put the values in the formula, you will get the answer. So I am sure that you guys must have been getting the idea about how to approach these type of question, how to solve these questions. So most probably you will be able to do the questions in the assignment. So I think I should go directly to the quiz question of the last run so that you can have a good understanding, and then if time permits I will come back to the theory portion. So not much theory is left actually. So basically what I wanted key, yeah, only impulse and design a Pelton wheel. So this question you can do at home. Design a Pelton wheel. Okay. So performance. So okay, we'll now we'll go to quiz questions. These are very easy questions compared to whatever question we just solved. So I want you guys to don't miss any of these questions. So I think this is numerical question. You just have a numerical question. So let's move to this. So let's remove this diagram. Actually, this is from previous wind turbine. Okay. So yeah, in India, this questions you should answer these questions. So in India, small hydropower plant ranges from small hydropower plant. So yeah, remember the first slide which I taught you guys. So it ranges from 2 megawatt to 25 megawatts. Okay. So correct answer is answer C is the correct answer. Okay. And let me check if I can if I can show you guys how small power plants actually look like. Small hydro power plant. Okay, so do we have a small power plant here? Uh, this is 4-bay powerhouse. So yeah, 4-bay looks like this. Okay, so the flow, the temporary reservoir is there. This is penstock and this is powerhouse. Okay, got it. This is one of a small hydroelectric power plant. So you can see this is not like a very big dam or something. This is not a very big dam or something which you see in like Teri Dam, Farakka Barrage, or in South you can see various dams, big dams are there, but like dam on Hirakud Dam, dam on Godavari, Narmada, Sardar Sarovar. Okay, these are very small, so these can be used to produce electricity. So this is one of the example. This is kind of front view of these small hydroelectric power plants. Okay. So I think if I could, this is like tail race or something. So mini hydropower, you can see here. Okay. So okay, mini hydropower is under discharge collected in the catchment area for 1 day. So this is a easy question. So I think you guys will be able to do this question. So let me do it for you only. So discharge collected for yeah. So you have meter cube per day. So discharge 2 kilometer area. So you need to convert it to the meter square, 2 into 10 to power 6. And but I think this is given for 1 day. So I think this is not needed actually. Discharge itself is given 5.5 meters cube per second. So you have to collect it for 1 day. So multiply it by 24 into 3600 into 365. Not 1 day only. So 5.5. This is 472500. Okay, 475200. So this is the correct answer. The function of weir is basically to regulate the flow of water for stable operation. So weir something looks like this or okay. So weir notches are there. So yeah, there are various type of structures that actually regulate the flow. So when you build a dam, the structures are very much required to have a constant flow of. So to regulate the flow, the weir is there. Cavitation occurs when the pressure of turbine is higher than atmospheric pressure. Wrong. Water in the turbine leaks due to pressure difference. Wrong. The pressure of water falls below vapor pressure in the turbine. This is the correct. Okay. So reason what happens cavitation? Cavitation is a phenomena. Okay. This is a phenomena. What happens when pressure falls below vapor pressure? So there are bubbles are formed. Okay, vapor bubbles are formed. So these bubbles travel through water, and then when it strikes a high pressure zone, like near the turbine or something, a solid surface, so these bubbles actually get broken down. So whatever vapor pressure is there is released, and then it does have an impact on the turbine blades. So erosion of turbine blades can be there. So that actually have a very negative effect on the performance of turbine also. So these cavitations should be avoided. Apart from that, it makes the turbine blade unable to operate freely or efficiently. So these turbine blades has to be changed actually. So that's why we have a lot of studies, lot of research going on to prevent this cavitation in the hydroelectric. Not only a cavitation is a problem in hydroelectric, but also in steam power plants also. Cavitation is a big problem. So one example of cavitation which I can give is like let me show you here itself. Like one example of cavitation in it's near the river course. Right. Cavitation due to river. So if I could have a example where I could so yeah this is kind of a corrosion which is due to the cavitation. It does look like this. So when you have a boundary wall near a river, so when flood comes, so flood can strike or waves or something, so they have a small bubbles that can actually strike down the surface and then uh, put a dent on the surface. So these can damage actually have. So this does look like this cavitation. Okay, so this is one of the example of cavitation on turbine blades. So this has to be avoided because they actually raise up the cost of operation also. Then we have this function of ELC. Basically, ELC is to supply constant electric load from the generator of the hydroelectric power plant. So earlier the governor is there to regulate the flow. ELC actually matches the load demand with the whatever power the generator is producing. So if load demand varies, it does varies throughout the generator. So varies at the generator so that it can be met. So to supply constant electrical load from the generator of the hydroelectric power plant. So correct answer is answer A. Okay. Now this will be I think we should have first question one. So solve this question. I think this type of question was actually done by you guys. So it will be very easier for you guys to actually calculate this turbine if this expected power output. So just calculate it guys and tell me the answer. I want the proper calculation actually for this. So no shortcuts, nothing. Proper calculation and answer. Because head is given, everything is given. You just have the turbine efficiency and generator efficiency. So let me write the formula also. Rho G H Q. Okay. And then answer is in kilowatts. So you have to divide it by 100. Sorry, 1000. Okay, so did you guys solve this question? Wait. Yeah, 785. Okay, Jayesh has said 785 is the answer. So yeah, that's correct answer. So it's basically rho GHQ. You have to put the values and multiply it with generator and turbine efficiency. Okay. So what are the next questions? Six we have done. Okay. So after solving this, we'll go to this question. So match the following: Francis turbine. So Francis turbine is a kind of, okay, it's not asking a kind of below head or this head or this head. So first is pellet turbine. So it does require a very high head actually. So which has a kind of high head, like intermediate type of head, pellet turbine, because the water jet strikes onto the surface and then it moves. So pellet turbine. It kind of impulse turbine. So I think this is the correct answer, 60 to 350-meter head. And then we have Francis turbine A. Sorry, wait. Okay, wait. Pellet turbine has a high head, that is the max head in between these two is basically this one. Okay, I just forgot to see. I was like, this is more less than 350. So this is Pelton turbine because it is an impulse turbine. So for any impulse turbine, a very high head is required. And then we have Francis turbine. So Francis turbine operates in intermediate type of head. Okay, so that is 60 to 350. And then Kaplan turbine. So Kaplan turbine, Francis turbine is kind of reaction turbine, and Kaplan turbine is like axial moving turbine or something. So it does a if there is low head, like in case of this small hydropower plant, so Kaplan turbine can be one of the option there because it does have a very low head there. So the correct answer is A2 B3 C1. A2 B3 C1. Okay, this one. So okay. So now solve this question. Should I give the formula also for this question, or you guys will be able to do it by yourself? So it says hydraulic power plant, the discharge, that is Q, is given, net head is given, turbine operates at a speed of 120 rpm, N is given, the turbine efficiency is given, NT, number of propeller turbines you have to calculate. Okay, a maximum specific speed is given, ns is given. So you know the formula, ns equal to n into p upon head to power 5 by 4. Okay, so you know ns here, you know n here, you know h here. So you will get a p value from here, and another p value you can get from rho g h cube. That is the power in the water itself. So you will get power from turbine and power from water. So you divide it this from this, so you'll get the number of propeller turbine that can be installed here. So use this formula. Tell me the answer correctly. Okay, guys, did you solve it? Let me see if you guys are able to solve it. No? क्या हुआ? क्या हुआ? Okay. Okay, let me solve it then. So first thing is that you need to calculate the power from rho GHQ. Rho GHQ. So rho is 1000, 9.81, H is 20, Q is 75. So that comes out to be around 13243 something kilowatt. Okay, so this is in kilowatt, so this will be cancelled. Okay. Hello. Yes, yes. Okay. And then another one is NS equal to N into root P H 5 by 4. So you get a power from here also. NS, 310, 120 root P, head is 20 to power 5 by 4. So this comes out to be around 310 on 120 and 220. Okay, and then you square it. That is 11938. Okay, this kilowatt. Now this is the power in the water. This is power produced by one single turbine. So now you want to know the number of propeller turbines. So just divide it. So this comes out to be around 1.1 or 2 something. 1.1 I guess. So that is something around one turbine. Okay. So this is how these type of questions are solved. So you just have to put the formula. You just have to apply a trick, like just understand what question is asking. Then you will be able to do it. Okay. It is done 9. Calculate the specific speed of the turbine which produces this power, this RPM, this meter head. The specific speed NS N root P H 5 by 4. You need to calculate NS. N is given, P is given, H is given. Okay. So calculate it, guys, and check if the answer is correct. Whatever you are getting is actually the same answer on the slides. Answer is 82 point. You got the answer? Okay, so I think you got the correct answer. Then this is the correct answer. Okay, so now you guys understood now. You just have to apply the formula and get the answer. So these type of question can be easily done. So don't panic from the question, just understand the question, what question is asking. So this is one of the good question I would say, and this is kind of normal kind of question. Just put the formula and answer this. Okay, now this you have to do. I think this question was done in like in the I think when I was talking theory things. So this was one of the question, like average capacity what available for power generation meter cube per year. So it is asking in meter cube per year, not in meter cube per second. So this you can easily do. Okay, so what you have to do, catchment area into 10 to power 6 meter square, and then this average rainfall, let's say R upon 100 to convert it into meter, and then 20% is loss, so zero point 0.8 is what you are getting. Okay, so this is what you have to, and then you don't have to divide it by that 24 into 360 into 3600, because the average rainfall for the locality is generally for 1 year. Okay, so calculate it. Into bar 9 na, so I think this is marked here, correct. 2.56 into 10 to power 9 is the correct answer. Okay, then the function of draft tube is, so I think I explain the function of draft tube. So this is the draft tube. What happens, this one is the A1 area, this is A2 area, the velocity here is V1, and this is velocity here is V2. So area is increased, so this is less area, this is more area. So similarly, due to continuity equation, A1 V1 equal to A2 V2. Okay, so velocity has to match it. So velocity will be more here less here. So if velocity is decreasing, then kinetic energy will decrease 1 by half mv square. Then that kinetic energy will transfer to pressure energy. So there is high pressure here, so there is high velocity low pressure here. Okay, and low velocity high pressure here. So to correct answer is to transform the kinetic energy of water jet into high pressure flow for discharge into the tail race. Okay. Yeah, sure. In the turbine blades, yeah, correct. Actually, it does help in preventing cavitation in the turbine blades. It, and this option is also right. I won't say, but the major function of draft tube, if you see the function of the draft tube, is to actually convert the kinetic energy of water to the pressure energy. But one of the, because of this conversion, it also helps in preventing the cavitation of the turbine blades. Advantages of draft tube. Okay, so it is not a function, it is advantage. Speed governor is used to, basically speed governor what it does. So if you have like electrical demand, like electrical supply has to be given. So based on that feedback, a speed governor regulates the flow of like flow of water into the turbine. So let's say this is turbine, and this is flow of water. So they, and there is this electrical demand here. Okay, So based on this demand, so if there is a high demand, then more water is to be supplied here. Okay, you know Q, rho g HQ. So if Q is increased, power will be increased. So more water. So this is what speed governor does. It actually regulates the quantity of flow of water through the runner in proportion to the load. So whatever load is there, in proportion to that, it regulates the supply of water. So correct answer is A. So I think most all the questions are done. Yeah. Any questions from the quiz are remaining? This is also done. This is also done. This is also done. So okay. So I think all the questions are done here for the quiz. And if there is anything which you want to ask, so already there is 150 is there. I think 10 minutes are there. So if any question, anything which you want to ask, which you cannot understand, so please feel free to ask now. And then we, huh, huh. Same. In final exam also this type of question will be asked. Okay. So if, hmm. Okay. So where do you have your job? Okay. So that's a good thing now. So you just having, I think, brushing up some new things and having expanded knowledge about this. So don't worry if you are okay. Hmm. Yeah. Okay. So if you like if you go through these quiz questions and try to solve them by yourself, I think most of the exam question you will be able to solve that. Okay. And then we have this interaction session. Me and Kapil are actually conducting on Fridays and Tuesday regularly. So we try to solve these previous year quiz questions so that you guys can have a familiarity about how these questions has to be approached. Because all these questions has to be solved by yourself. We just provide a familiarity, like, yeah, this is the way you approach a question. And these questions are not so hard, you will see. Very few of them are like tricky. So this can be easily done. Okay. So if anything else, any concept or anything which you want to ask, so always welcome to ask. Solar. So yeah, you can ask if there is some theoretical question which you want to ask. So, yeah, you can. Numerical questions also, if I will be able to answer, because I forgot solar. I think it was first week or second week. But you can ask. I will surely. Okay. So if there is something like if some session are missed or something, so no problem. You can ask in the upcoming session. So we'll discuss that if some of the it doesn't involve a very big discussion or something. If some theoretical thing is to discuss, we can discuss that on that. Otherwise, you can always take a screenshot, post it on the discussion forum. So regular TAs are there for the course, so they will also help. Okay, okay, no problem. Mm, so I think we have done this. Okay, so this was I was trying to explain the impulse turbine. So, I think we had this, na? Okay, we solved this. Okay, this I converted to centimeter. Okay. So there are different types of turbines. So if you have a mechanical background, I think you must have got a good idea of previous knowledge itself, that there are types of turbines which actually produces power. So one of them is like impulse turbine. So impulse turbine, I will say, like, if you have seen something like Chakki in Punjab, we have something like in older age or something in Rajasthan especially, we see these type of chakkis. Like there is a water reservoir, or you say water well, strip well is there, and then there is chakki. We say chakki, and then there are buckets around those chakki. So it moves like this, and then It takes the water and then forces into the tail race. So similar on those criteria, this impulse turbine works. What it happens? So it does have a turbine and there are some blades. So water strikes those blades and make it move like a wheel. So because of this movement, a shaft is connected and that shaft goes directly to the generator. So that generator, the induction coils are there and everything is there. So that shaft also moves and generates electricity. So this is how it works like. Okay. These are moving rotors. So these moves and then the electricity is generated. So one is this single movement like single phase strike, or maybe there is a water flowing from here also, that also strikes here. So there are different types of impulse turbines. Okay, so this can be a Pelton wheel. That wheel which I was talking about for water wheel or something. So that is called Pelton wheel. So reaction turbine. So we remember this impulse turbine. This is like this. So a water jet is that strikes the blades and it creates an impulse that moves the blades in a rotary direction. But in reaction turbine, what happens? It is something like this. So there is a rotor and the water is there. So if something is pushed at a very high velocity, so then it will have a negative force because of Newton's second law of motion, that any action will have a reaction. So on similar laws, this reaction turbine actually works. Okay, so these reaction turbines are of two types. One is like not two types. You can say Francis turbine is a type of reaction turbine, and similarly we have this Kaplan and I think these are not in the slides. So Kaplan and axial turbine also there. Axial moving turbines are there. Okay, that also work on those concepts. Then there are performance parameters, like when you are talking about turbines, so then there is some performance parameter on which you talk about, like speed, discharge, how much is the speed on which the turbine moves, how much is the discharge that it can handle, and then how much is the power. This is the main criteria which is produced. Okay, this is what is basically when you are talking about a performance of hydraulic turbines, so these criteria has to be taken into account. Okay, so I think for today lecture, all the slides have been discussed. So if there are any queries, please feel free to write to me on this email ID. Otherwise, you can always ask in the upcoming lectures. Or you can always put your questions or any doubts which you have on the discussion forum. So that's all. That's all from my side. So we'll meet again at next Tuesday from 7 to 9. Thank you, Jess. Thank you for attending this session. I think this session must be helpful for you. So you guys can leave the meeting. Okay. So one more thing is there. These sessions are recorded, so we upload this session in the YouTube, and the link are shared with you guys on the NPTEL portal. So you can go to the problems. Okay, one more thing. So you must have missed some previous sessions. So there is problem solving session reminder tab is there. When you open the NPTEL, there is problem solving session tab is there. So click on that. All the links and all the slides are shared with you guys. Okay, so you can go through the slides and videos also. Okay.